In the last section, we introduced the Schrödinger equation. We discussed the meaning of the wave function and some postulates in quantum mechanics. In this section, we're going to apply Schrödinger equation to the simplest case, and that is the particle in a box. Let's go over the Schrödinger equation. On the left side, we have this kinetic energy operator, which is the second order derivative of the wave function. The potential energy operator, which is the potential energy multiplied by the wave function. On the right side is the total energy times the wave function. This Schrödinger equation is the same when we apply for any system. The difference is the form of this potential energy. Sometimes this potential energy makes this Schrödinger equation too difficult to solve. And therefore, the simplest case is when the potential energy is zero. And this makes the Schrödinger equation very simple to solve. We're going to show you how to solve this Schrödinger equation without the potential energy. But first, what does this mean when the potential energy is zero? Potential energy is a measure of interaction. For example, the gravity, you have a potential energy, mgh. So, if potential energy is zero, we can say the particle is a free particle. No interaction, it's a free particle. So do we have a system in chemistry that is free? In fact, we have some systems that we can consider they are free, but only in some locations. And they are not free on other places. And so we can say they are restricted in a certain area. And we also call this particle in a box. That means they are free inside this box between 0 to A, but not free outside the box. Let's look at a system in chemistry that is can be considered as a free particle. One of the systems where we can apply particle in a box model to is the conjugated dyes. Conjugated dyes are the molecules contain alternate double bond, single bond. These molecules show bright color, and the color depends on the number of double bond. These properties can also be analyzed by measuring the absorption in UV light. So different number of carbon and the double bond absorb at different wavelength. And this will give you different colors. So in theory, using quantum mechanics, we can calculate the molecular structure, the energy levels, and we can predict the absorption of the wavelength, and therefore predict the color of the conjugated dyes. But first, why can we apply the particle in a box to these conjugated systems? To understand that, we need to look at the double bond. In organic chemistry, you learned that carbons in double bond are sp2 hybridized. A carbon atom contains a 2s orbital and 3 2p orbitals. And these are 2px, 2py, and 2pz. Before this atom interact with other atoms, it first hybridizes first. That means the s orbital and the 2 of the p orbitals mix and forms 3 equivalent orbitals. And that's why it's called sp2 hybridization. Because these 3 orbitals are equivalent, they form a trigonal planar geometry, which has 120 degrees from each other. So these blue colored orbitals represents these 3 sp2 hybridized orbitals. They are in the same plane and 120 degree. Now there's a pz orbital that is not hybridized, unused, and this is still here. That's the red one, which is perpendicular to the plane. When two carbons approach each other, each of them uses sp2 hybridized orbital to form a bond. At the same time, the unhybridized p orbitals also forms a bond. Note the difference. Between the sp2 hybridized orbitals, the interaction is like head to head. The overlap is large. So the interaction is very strong, and this is called the sigma bond. But between these two p orbitals, the interaction is look like a shoulder to shoulder interaction, so it's much weaker, and this is called the pi bond. Sigma bond is usually much stronger than pi bond, so the two electrons in this sigma bond is localized, cannot move, but the electrons on the pi bond is weak, they can move between the two carbons. Here's another drawing of the double bond. Okay, so if you have a double bond, one of them is a sigma bond, and the other is pi bond, is between these two p orbitals. That's a pi bond. Electrons are loosely bonded, can freely move. And now, if you look at a conjugated system, you have more than one double bond. We can also draw each of them have a p orbital. So the interaction is between all of them. And the electrons, as we see, are loosely bonded, and they can move between all these carbon or nitrogens in the whole system. Okay? But these electrons, although they are free to move along this molecule, they cannot get out, because the electron attracted by this nucleus, so they cannot get out of the molecule. But you can consider them free along the molecules, and that's why we can apply particle in a box model to the conjugated systems of the pi electrons. In summary, a conjugated system is a one-dimensional space of some length L for pi electrons that can move freely along this molecule. The potential energy is considered constant or even zero, like this blue color. The potential energy becomes infinite at two ends. This ensures electron is restricted inside the molecule, but cannot get out. In reality, the potential energy is not constant but oscillate, like this red color. This is because the positive charge at the locations of the atoms. Now remember, when we study gas phase, we start with ideal gas law, assuming there's no intermolecular interaction. And then we can add attraction force, repulsion force to make it appropriate for real gas. Same thing is here. We start with the simplest model, and that is particle in a box, assuming there's no potential energy inside. We apply Schrödinger equation, solve the Schrödinger equation, and find the electronic energies orbitals of this molecule, and then we can calculate the absorption of light. Here is the Schrödinger equation with potential energy 0. In order to make this equation look simple, we divide by both sides by the constant negative h bar squared divided by 2m. In other words, we move this to the right side, so we inverse it. And then we move this to the left side, so negative becomes positive. And because these mass h bar, e are all constant, we can replace all this by one constant, let's say c. And later we'll see that the sign of this c have great impact on the solution, and therefore we want to emphasize the sign of this c, whether it's positive or negative. And you can see every constant here are positive, mass, h bar, and e, and therefore c must be a positive number. So instead of use c, we use some constant squared, let's say k squared. Okay, anything squared is a positive number, so we combine all these and write as k squared. So the equation now becomes this. Okay, you have all constant combined here as a k squared. 2 represents is a positive number. Now you are familiar with, instead of psi, you might be more familiar with y. So this equation you can also write as second derivative of y plus k2 times the function y. So at this point, the Schrödinger equation becomes this second order differential equation. So the next slides, we're going to see how we can use calculus to solve this equation. A differential equation like this one, where a, b, c are all constant, is called second order linear differential equation. The solution to this equation has the form e to the rx. In order to find the r, we plug in this into this equation, and then we can solve the r. So let's first calculate the derivative of this solution. So the derivative will be r times e rx, and the second derivative will be r squared e rx. Now plugging all this into this equation, differential equation, so you should have a times second derivative is this one, r squared e rx, plus b times first derivative is this one, r times e rx, plus c times the y itself, which is e rx, equals 0. So all of them has erx, 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 and therefore you have a times r squared, b times r, c is 0. And this is called a characteristic equation. So whenever we have a second order linear differential equation like this one, we can always write this characteristic equation in which we replace second derivative by r squared, first derivative by r, and then y replaced by c, by 1. So c times 1 equals 0. And from this we can solve r. Okay, we solve r and put back into this equation, and that's the solution for this second differential equation, linear differential equation. So let's do example. This is a second order differential equation. So a is 1, this is a, b and c is -3. In order to solve it, we replace this equation using a characteristic equation. So y's second derivative replaced by r squared. So r squared, and the first derivative by r, 2r, and -3, all right, equals 0. So that's the characteristic equation for this differential equation. To solve this one, we factor it into r plus 3, r minus 1. Okay, so this is equivalent to this one. But this says that the two product is a 0. So this will be 0, which says r equals -3. And this is 0, so r equals 1. And now we put back into this equation. So the solution to this one is y equals e to the rx. R is -3, so -3x. And it can also be e to the x. So both of these are the solution of this second differential equation. Now you can put back and see if they make this left side 0, and to prove they are solutions. In general, the solution will be a constant C1 times the first solution plus C2 times the second solution. That's the general solution for this differential equation. All right, now let's go. We are ready to solve this Schrödinger equation for the particle in a box where the potential energy is 0, okay, or just the free particle. This is the Schrödinger equation for free particle. Okay, so we replace y second derivative by r squared. We have no first derivative, so there's no b, and we have k squared equals 0. Okay, that's the characteristic equation. So how do you solve this one? Okay, let's have two examples. One is, let's say r squared plus let's start -16. All right, so r squared will be 16, right? You move this to right side, negative becomes positive, so r will be positive negative square root 16, which is negative positive 4. All right, so that's simple. What about r squared plus 16? Okay, do the same thing. R squared equals -16, and r should be positive negative square root negative 16. Okay, so you see, square root negative 16 does not have a real number, and so it's imaginary. So it's positive negative for I. Okay, from these two examples, we can see the sign of this k squared, of this number is very important. If it's negative, the solution is real. If it's negative, if it's positive, like here, then it's imaginary number. And we showed that this number is always positive. That's why we use k squared, remember? And therefore, the solution will be r will be positive negative square root k negative k, just like here, so that will give you positive negative ki. All right, and then we put back into this equation, so you have two solutions. One is e to the kx, ikx, all right, or e to the negative ikx. So the general solution for the Schrödinger equation with no potential energy is C1 times eikx plus C2 times e to the negative ikx. So many of you may maybe not comfortable with imaginary number, but remember, wave function does not has a physical meaning, and the important thing is when you square it, then when you square or use conjugate times it, that gives you the probability. So imaginary number is fine for wave functions. We just solved the Schrödinger equation for free particle. The general solution is C1 e to the ikx plus C2 times e to the negative ikx. We can find kinetic energy and momentum of this particle. For example, to find the kinetic energy, as we did in the last section, we just apply momentum operator operates on this function. For example, for this function, the momentum gives you h bar times k, but for this one, it gives you negative h bar k. So the particle move for this function, it moved to the right side, but this to the right side, to the left side. And therefore, if you measure kinetic momentum, sometimes you get negative, sometimes you get a positive. Now, what about kinetic energy? To find the kinetic energy, we apply kinetic energy operator, which is the second order derivative. And here is the solution, the wave function. And when we do that, we get the function back. And the number in front of it is the kinetic energy. And in this equation, k has no restriction, means that it can be any value. So the kinetic energy of the free particle can be any value. Now later, when we restrict this free particle in a certain location, that means in a particle in a box, then the energy becomes quantized, which means only certain energies are allowed. So this is the general solution to the Schrödinger equation for particle in a box model. We are now going to modify this equation using Euler's equation, which says e to the I theta equals cosine theta plus I sine theta. So e to the I kx should equals to cosine kx plus I sine kx times C1, and e to the negative ikx should equals to cosine negative kx plus I sine negative kx. And you have a C2 here. Okay, now cosine negative kx should equals to cosine kx. All right, and the sine negative kx is negative sine kx. Okay, so combine cosine kx, so you have C1 plus C2 cosine kx, and combine sine kx, so you have C1 minus C2 times I sine kx. Okay, now C1, C2 both constant, we can use one constant A, cosine kx, all right, plus this C1 minus C2 also constant, and I. So we put together as B sine kx. Note that here B is an imaginary number. Okay, so the general solution now becomes A sine kx plus B cosine kx. And later when we solve this, we should remember the k is related to energy, because the constant 2me divided by h bar squared, altogether we said is k squared, right? So therefore, when we have the k, we can calculate the energy using this equation. Let's look at the particle in a box model. The potential energy is 0 inside the box. The particle is free inside the box, and we already have the solution, A sine kx, B cosine kx. Imagine the conjugated system where the pi electrons can move freely inside the molecule. This is the wave function of those pi electrons inside the molecule. But the electrons cannot get out of the molecule, so so the wave function must be 0 outside. This is because wave function is a measure of probability. So if the particles cannot get out of the box, then the wave function has to be 0 outside. So here the wave function is 0 outside. Now inside it's sine, cosine, so it can be something like this one, but at the two ends it must be go to the 0 because wave function is continuous. So if it's 0 everywhere outside, at the two ends it must also be 0, and this is called the boundary condition. At the two ends the wave function goes to 0. So wave function when x is 0, and that's this point, wave function is 0. The wave function when x equals a, that's this end, also goes to 0, so that it continues to be 0 outside. And we are going to apply these two boundary conditions to this wave function and to see what happens when we apply these two boundary conditions. Let's look at the first one. When x equals 0, what is the wave function? Apply this to this one. So you have a sine 0 plus b cosine 0 when x is 0. Now sine 0 is 0, so this goes to 0. So you only have b cosine 0. Now cosine 0 is 1, so the wave function becomes b. At this left end, the wave function becomes b. But the boundary condition says it has to go to 0 because the wave function is continuous and outside is 0. So at this point it must be 0. So this gives b 0. And therefore, in order to meet the boundary condition on the left side, the solution becomes a sine kx. The reason is b 0. B has to be 0 to meet the boundary condition on the left side. And so the wave function now only becomes a sine kx. This is the solution when it meets the boundary condition on the left side. Now we are going to look at the right side. So here is the wave solution of the Schrödinger equation if it meets the left side boundary condition. Now let's look at the right side. Wave function at xa is also 0. So when x equals a, this becomes a ka. So a sine k. This is the wave function when x equals a. But this has to be 0 because outside is 0. So if it's continuous, at this point it must be 0 too. For this to be true, sine ka has to be 0. Alright, so what kind of ka to make sine 0? It can be 0, it can be pi, okay, sine pi is 0, sine 2 pi is 0, 3 pi is 0, and therefore the general solution is ka equals n pi. And therefore k is n pi divided by a. What is n? N can be 1, 2, 3, or it's just integers. Goes on. Okay, so you see the quantum number here, 1, 2, 3, 4, comes naturally due to the boundary condition. Okay, when the wave function meets the boundary condition, it has to go to 0, and the solution is a series numbers, and that induce the quantum number 1, 2, 3, 4. And remember, k is related to the energy. Okay, so it's this equation. K, remember this equation? So k squared is a combination of those numbers include the e. So e can be calculated if you know k. So here k is n pi divided by a, and therefore you can calculate the E. Alright, so E is h bar squared divided by 2m times k squared. K is this one, so square this one. And combine numbers, you have n squared h squared 8ma squared. And note that n can only be 1, 2, 3, as here pi, 2 pi, 3 pi. So n can only be 1, 2, 3, 4 integers. That means the energy now is quantized. It can only have certain numbers. 1 h squared, 2 squared h squared, 3 squared h squared. So energy now is quantized. Similarly, the solution a sine kx, okay, k is m pi divided by a, so m pi xa. So the wave function can only be a sine pi x over a, 2 pi x over a, 3 pi x over a. So by applying the boundary condition on the right side, the energy is quantized. The wave function also quantized, means only certain allowed energy and the wave functions are possible. These are the solutions, final solution when we apply two boundary conditions. This is the wave function for the particle in a box. In this equation, A is the length of the box, x is the location of the particle, and n is a quantum number, can be 1, 2, 3, 4, 5, any integer. And what about a, this constant a? In order to find the constant a, we use the fact that the wave function in the whole range has a probability equals 1. And that's actually called normalization. So square of the wave function integration in the whole range is 1. Okay, so plug in the wave function and let's integrate this one. Now, one way to do it is to find the standard integer, which says sine alpha x squared integration should be half x minus sine 2 alpha x divided by 4 alpha. And so compare with our equation, so m pi divided by a should equals to should be the alpha. So replace all the alpha by this m pi divided by a, and you should get the integration a divided by 2. Okay, so please spend time and see if you can get this number. And from this, we can calculate a. Constant equals square root 2 over a. And therefore, the normalized wave function now becomes square root 2 over a times sine n pi x over a. In summary, these are the solutions to the Schrödinger equation for a particle in a box. The energy is n squared h squared divided by 8ma squared. N is a quantum number 1, 2, 3, 4. That's the integer. Wave function is square root 2 over a sine n pi x over a. N again is a quantum number 1, 2, 3, 4. The quantum number comes naturally when we solve the Schrödinger equation. In order to meet the boundary condition at the two ends, the wave function has to go to 0, because the wave function is continuous and is 0 outside. They must be 0 at the two ends. It's not an assumption that the energy is quantized. You don't need to make any assumption as long as you use the Schrödinger equation and apply boundary condition. It comes naturally. And when we plot it, here the lowest energy when n equals 1, the wave function is sine 1 pi x. So here is a half wave. The second wave function n equals 2, you have one wave. And the third one, you have 1.5 wave. So when you increase the quantum number n, the wave length decrease. So this is one wave, this is 1.5 wave, this is 2 wave. So wavelength decrease and the curvature increase. Curvature is a measure of second derivative. This is about kinetic energy. So kinetic energy increase when you increase quantum number n. Also notice that the number of nodes, which is the wave location where wave function becomes 0. So here wave function becomes 0. For the second one, you have 1 nodes. For the third one, you have 2 nodes. For the fourth one, you have 3 nodes where the wave function becomes 0. And in general, it's n minus 1. For example, for the first one, n is 1 minus 1 is 0. And you have no node for the first one. And for the second one, 2 minus 1 is 1. So you have 1 node. So in general, you have n minus 1. And the number of nodes increase. Okay, 1, here you have 2, you have 3. So number of nodes increase with energy. All these results not only apply to the particle in a box, but also for many other complicated systems. And so you see the particle in a box model is very useful and educational. It's easy that you can solve, but the solution and the way the quantum number comes out and the results are also true for other complex systems where you don't have a chance to solve. It's too much mathematics. But here we can see how this is solved, and we also see how quantum number comes out and the results here. Let's now focus on this wave function. So here is the normalized wave function, and these are the plots for n equals 1, 2, 3, 4. So what do this wave function mean? As we know, wave function does not have a meaning. It's the square tells you the probability. So we need to square all these wave function. And these are the squared of this wave function. Okay, so let's look at the second one. All right, so you have a positive here, you have a negative, but when you square it, all becomes positive. So you have a positive, also positive. Similarly, for the third one, positive, negative, positive. But when you square it, it all becomes positive. Okay, so now what does this mean? Remember, these tells you the probability. So for the first wave function, which has lowest energy, the most probable place is here in the center. This gives you the highest probability. For the second one, the most probable place is here and here. All right. For the third one, the most probable place is here. Now, let's imagine you have a double bond. As we see in the beginning of this section, each carbon has a sp2 hybridization, the pi bond. Okay, each carbon contributes 1 p orbital with 1 electron to form pi bond. So you have 2 pi electrons. These 2 pi electrons goes to this orbital, lowest energy orbital. And this model tells you the most probable place is in the center, and that means the most of the time the 2 electrons are in the center of this double bond. How about the 2 double bonds? Okay, 2 double bonds, now you have 4 pi electrons. Okay, so 4 of them. According to Pauli exclusion principle, each orbital can only have maximum two electrons. So this one you have 2 electrons. The next 2 goes to here. And therefore, for 2 double bonds, you have total 4 electrons. You need to look at this orbital. Okay, this is called the highest occupied molecular orbital in this case. According to this drawing, the most probable place is here and here. In the center, you have no electron, you have nodes. And that's exactly what we see here. Most probable place here, here, and no electron here. So you have 2 double bonds here, but no electron in between. That's the pi electrons. What about a molecule with 3 double bonds? If you have 3 double bonds, each carbon has 1 electron, pi electron, so now you have 6 electrons. And the Pauli exclusion principle says 2 here, 2 here, and 2 here. So we are looking at this molecular orbital, and it says most probable place here, here, here. You have 2 nodes. And same thing is this model. You have most probable here, 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 and nodes here, nodes here. And that is consistent with the hybridization model. And you see this, although the particle in a box model is very simple, all right, but the results actually is consistent with what we observe in this simple molecular or organic conjugated system models. The wave function drawing in the last slides shows that first wave, you have half wavelength. Second, you have 1 wavelength. The third, you have 1.5. If you draw the probability, square it, the most probability for the first one is in the center. For the second one is here and here. Third one, you have here and here. So if you increase the numbers, you are increasing the wave. So the most probable place becomes more uniform. And this shows in this diagram. And this is n equals 1 for the red one, and the blue one is nx50. And you can see the n equals 1, the most probable is in the center, but when n equals 50, the most probable place can be here, 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 many, many places. So the probability density becomes more uniform as n increases. This reflects the classical results. A particle bouncing between the walls spends equal time at any points. And these results not only apply to a particle in a box, but also for all other quantum mechanical systems. And this is called the corresponding principle. As high quantum number n increase reaches classical results emerges from quantum mechanics. Now let's look at the equation for energy. N squared, h squared divided by 8ma squared, in which n can be 1, 2, 3, 4, an integer. So what is the lowest energy? The lowest energy when n equals 1. And the important thing to realize that the lowest energy is not 0. And this is very different from what we see in our everyday life. Okay, when we run, the energy can be anything, can be 0. But here, the lowest energy is non-zero, and this is called a 0-point energy. Many quantum mechanical system has a 0-point energy, which means the energy is not 0. The lowest energy is non-zero. Okay, so what about the separation between the two energy level? So if you draw energy level, this is n equals 1, n equals 2, n equals 3. So in between these two, all right, the energy, so for example, this is n plus n, this is n plus 1. So the difference, you use this equation. So that's the energy for n plus 1, and this is n. The difference is here. All right. Important thing here you see is inversely proportional to the n squared, a squared. A is the length of the box, the particle box. So when you increase A, you decrease the separation. The delta E becomes smaller when you increase A. Imagine the A increase becomes a centimeter. Their delta E is so small that you can think about it as continuous, not quantized. And therefore, the separation decreases as the length of the container increases, and is very small when the container becomes a macroscopic dimension. So if it's a macroscopic dimension, the separation is too small to be observed. Okay, so you can ignore the quantization when the dimension becomes macroscopic. We have solved the Schrödinger equation for 1D box model. And now we know that the particle in a box has certain allowed energy levels. And now let's look at an example. Calculate the first electronic transition energy for butadiene molecule. Butadiene has 2 double bonds and 1 single bond. And as we've seen, this is a conjugated system with each carbon contribute 1 electron of a p orbital. And these electrons can move freely along this molecular framework, but cannot get out of the molecule. So it's a 1D box. And the allowed energy level is described by this equation, n squared times h squared, Planck constant, 8 m mass of the electron, and A is the length. The length here is calculated by 2 double bond, so 2 times the length plus a single bond. Here you have a single bond 1.54. Now, because the atom is not just a dot, okay, so you have a radius, and therefore this part added together, we add one more bond. Okay, this bond takes care of these two parts because the atom is not just dots, they have sizes. And therefore, in this case, we have 2 double bonds, 1 single bond, and add one more single bond to take care of these two ends. Now, in different cases, the question may give you different way to calculate this box. You should pay attention to the instruction. So if we draw the energy diagram, this is when n equals 1. So according to this equation, is 1h squared. And when n equals 2, so 2 squared should be 4 divided by 8. H squared, ma squared, and that gives you half h squared divided by ma squared. And then this is n equals 3. Okay, now because we have total 4 electrons, 4 electrons cannot all goes to the lowest energy level. This is due to the Pauli exclusion principle. Each orbital can only hold maximum 2. So 2 goes to here, the other 2 can goes to the second energy level. And the second energy level here is called the highest occupied molecular orbital. And the one above it is called the lowest unoccupied molecular orbital. The electronic transition is between this highest occupied molecular orbital and the lowest unoccupied molecular orbital. And this difference should equal to the photon energy. When the photon, one photon absorb energy, it will go from here, highest occupied to lowest unoccupied molecular orbital. Now remember, different system, the HOMO-LUMO will be different. For example, if we're talking about 3 double bond, then each carbon has a 1 electron contribution, so you have 6 electrons. So 2 here, 2 here, 2 here. So then the third energy level will be the HOMO. And this fourth one will be the LUMO. And when you calculate the transition, you should calculate the difference between the third one and the fourth one. Now in this case, we have 4 electrons. So the second one is the HOMO, and the third one is LUMO. And therefore, the delta E is between the second one and the third one. So the energy of a third energy level minus energy of a second level. All right, plug in every constant, Planck constant, mass of the electron, the length of the box, and that gives you 9.02 times 10 to the minus 19 joule. And this equals Planck constant divided by the frequency. So you can calculate the frequency. So here the frequency is calculated in terms of inverse centimeter. And we'll show you how to change from the unit to inverse centimeter. But the point is, the calculated number is very close to the experimental data, 4.61 times 10 to the 4th power inverse centimeter. And this shows that even though this model, particle in a box model, is very simple and crude, but the results is actually not too different from the experiment. Let's come back to the conjugated dyes we introduced at the beginning of the section. Conjugated dyes are the molecules containing conjugate double bonds. Chemistry major student will do a Pecan lab. In this lab, you are going to be given a number of dyes. One of the dyes will have 3 carbons, like we draw here. 3 carbon, and the other one will have 5 carbon, and the other one will have 7 carbon. So we are changing the length of the box. The electrons, these pi electrons, can move freely along this box. The allowed energy is described by this equation, and we can calculate the energy separation between the HOMO and the LUMO for each dye. Okay, and from this we can calculate the wavelength of the light that will be absorbed for each dye. So in theory, we can predict the absorption of different dyes. And then we do UV absorption and see if the theoretical calculation is consistent with the experiments. In this section, we applied the Schrödinger equation to free particle where potential energy is completely 0. This makes the Schrödinger equation very simple to solve, and the solution, the general solution, is C1e to the ikx, C2e to the negative ikx. Using Euler's equation, the solution becomes A sine kx plus B cosine kx. In chemistry, we have some system that the electrons can be considered as free particles, and that is a conjugated system. But electrons cannot get out of the molecule, so it is considered to be particle in a box. Because electron cannot get out of the system, so the wave function outside the molecule is 0, and the wave function is continuous, and therefore they must be 0 at the two ends, and that gives you the boundary condition where the wave function is 0 at the left side, the wave function is 0 at the right side. Apply this to the solution, B has to be 0 to meet the boundary condition on the left side. And to meet the right side boundary condition, we find that the K can only have certain values. Ka must be pi, 2 pi, 3 pi, so K is quantized. K is related to the energy, and therefore the energy is quantized, all right? It's determined by quantum number n, and the wave function also is determined by quantum number n. We introduced the concept of UV visible absorption, the homolume gap, the 0-point energy, the correspondence principle. This model, okay, particle in a box model, is very simple yet very instructive. It has crude applications to conjugate hydrocarbons.